Hi guys, and welcome back to 7 Steps to a 7 in Olympiad Algebra. In the last video, we were looking at Olympiad style inequalities, and these don't show up very often. However, what we're going to be discussing for the next few videos, functional equations, are very common in math Olympiads. So yeah, we're going to be dedicating, I think, 3 videos to them. So let's go ahead and get started by first figuring out what exactly is a functional equation. And put simply, it's just an equation satisfied by a function. So for example, you could have something like as simple as f of x plus 6x equals 7x. This is a functional equation. And obviously, if you solve it, you get f of x equals x, which is the only solution. However, functional equations are usually much more complicated than this one, and some are way harder than others to solve. For example, here's a very hard functional equation from the 2017 IMO, and this was so hard that only a fraction of the contestants got full marks on this problem. So as you see, there's a huge difference between this functional equation here and this one over here. So the point is that functional equations can vary a lot in difficulty, and therefore they take lots of practice. Now, there's one thing important to note about functional equations, and it is that they are satisfied for infinitely many choices of numbers. So in a way, we basically have like infinitely many equations which we want to simultaneously solve. So for example, we have something like f of 1 plus f of 2 is equal to f of 3. And then we could also have info like f of 2 plus f of 4 is equal to f of 6. Or like f of 7 plus f of 8 equals f of 15. And the equations just keep going on and on and on. And you basically have like infinitely many of them in a way. So yeah, that's basically the main idea behind functional equations and what they are. So what is the basic framework of solving a problem in functional equations, which is abbreviated in FE by most of the Math Olympiad community? Well, here's a framework. So the first step is to find all the solutions that work. So for example, if you have a function f satisfying an equation, you could find like f of x equals 0 that works, f of x equals x that works, and so on and so forth. And the goal is you're trying to find all the solutions to the equation. And the first step of the problem is to try finding all the solutions you can. You don't need to prove that they're the only ones, but just keep trying functions until you get some that work. And then your goal is to prove that those are the only ones. And this is incredibly important because the set of solutions tells you what you should be trying. Because not finding a solution can throw you entirely off track, as we'll see in a bit. And the second thing that you should do is to plug some basic things in. For example, if the functional equation is from r to r, then you can plug in 0 for one of the variables because 0 is basically your favorite real number because it makes everything vanish. And so what I mean by plugging basic things in is try plugging in all like the standard things, quote unquote. And as I said earlier, you can also try plugging in 0 as much as you want to, unless you can't at all. And you can also plug in things like, for example, x equals 1, y equals 1, x equals negative y, x equals y, and so on and so forth. Whatever you think of at the top of your head. Now, all functional equations are not as simple as that, so you often have to try more articulate methods. Now, these articulate methods that I'm talking about here are basically learned over time. As you do more and more FEs, you're going to learn more and more of these methods. And you're often going to devise methods on the fly. Like, you could be faced with a certain problem, and you'll have to devise a method that you've never seen before based on your intuition. And those are for the super, super hard problems, so don't get intimidated. And that's basically articulate methods. We're going to talk about some of them later in the video, but some of them include like canceling terms from both sides and exploiting asymmetry. And a special case of this one here is to try proving statements about f. For example, it could be injective, meaning if f of x equals f of y, then x equals y. It could be surjective, meaning that f of x equals t has a solution for all t in the range or codomain. And other things could also be true about it. And finally, when you're super, super close to a solution, you want to try cleaning up the mess. And that's usually the final step. Now, this cleaning up the mess can usually be in the form of a pointwise trap, which we're going to talk about later in the video. Or it could be in the form of like proving f is strictly increasing or continuous, or using some well-known like property about functional equations. But the point is that there's often a mess you might need to clean up after solving it, like dealing with some special cases. And then finally, that ends up solving the problem. And then there's one last thing that you need to do in order to get full marks on the solution. And it is to, I'm going to go ahead and put this in red, check the function's work. And this is super, super important, because if you don't check a function works, then your solution is incomplete. Because suppose you show that all f must be linear, it's of this form. Then what if most of these linear functions don't end up working out? Like f of x equals, I think, 41x, suppose, could end up not satisfying the equation. So you might have to come up with something else or plug in. So you'd have to plug in this in order to make sure that it works, in fact. Otherwise, you're going to get a 6 out of 7 on your problem. And after all, this series is called 7 steps to a 7. So you want to try checking your function's work. All right, so that's the basic framework of a functional equation. And you'll see what all these steps mean as we progress later in the video. Now let's take a look at what is the simplest functional equation ever. And what I mean by simplest is most basic. And it is as follows. That f of x plus y is equal to f of x plus f of y. Now, we need to specify what domain we're working over. And we could say that we're working over real numbers, but as we'll see in a later video, we're going to get really... But as we'll see in a later video, things will become really, really complicated with this. So for now, let's go ahead and restrict ourselves to a very, very similar domain, actually. The rational numbers. So f goes from the rational numbers to itself. Then what must we know about f, if f satisfies this equation? Well, let's go ahead and see how each of the steps I outlined above play out. So the first step is to find as many solutions as we can. And for one, if the f was not there at all, then we'd have x plus y equals x plus y. So basically the f which doesn't do anything is a solution. And that means that f of x equals x works. And then we could also have that if everything vanishes, like everything on either side is 0 and all the f's disappear, then we get 0 is 0 plus 0, which is true. So that means that f of x equals 0 is also a solution. And then we might see what's going on here. And for example, you might see that f of x equals 2x is also a solution, because like 2 times x plus y is equal to 2x plus 2y. So in general, we have all of these solutions. And by just adding any constant in front of this, because 2 is not very special in this regards, we see that like f of x equals c times x, where this is in the rational numbers, is a valid solution. So now we have this entire family of solutions, and let's go ahead and assume that we found all the solutions. And if we find another solution, we'll have to edit our argument in order to make it work. And this gives rise to a general idea when faced with functional equations. And it is to check all linear solutions. Because oftentimes the writers of functional equations will make functional equations that have these linear solutions that behave nicely. And your job is to always check for them first. And if you don't have any interesting linear functions, then you can try moving on to quadratic, then cubic, then so on and so forth. Anyways, that's the first step in action, where we found all the solutions we could. And they're of the form f of x equals cx. So I'm going to go ahead and put that at the top. F of x equals cx. Now we have the second step, and that is to plug in as many basic things as we can. So first, let's see what happens if we plug in x equals 0. Then we get f of y is equal to f of 0 plus f of y. So that means that these guys cancel out, implying that f of 0 equals 0. So I'll go ahead and put that in the corner over here as well. F of 0 equals 0. And now let's see what else we can get. And this is already pretty useful. And if we plug in x equals 1 instead, we get like f of y plus 1 is equal to f of y plus f of 1. Whatever f of 1 is equal to. And that means that if we increase y by 1, as we do here, we increase f of y by f of 1. So in a way, this means that f of 1 is like the slope. And we know that slope kind of makes sense because we're looking at linear functions as our only solution. So because f of 1 is our slope, it makes sense to give it a special value, let's say c. Then we know that f of y plus 1 is equal to f of y plus c. So every single time we increase by 1, we increase the output by c. And now let's go ahead and try some more articulate methods. These are basically all the basic things we can try. So now we have step 3. I'm going to go ahead and put f of y plus 1 is equal to f of y plus c over here. Now we have some articulate methods. What can we do with f of 1 equals c in this equation? Well, because we know what f of 1 is, it makes sense that we can plug in x equals y equals 1, because we know that value and we can do stuff with that. And then we get f of 2 is equal to f of 1 plus f of 1, and that's equal to c, because it's c plus c. And let's see if we can try continuing in this way, because now we know f of 2. So we could plug in 2 here and 1 here, or 1 here and 2 here, and then get f of 3 is equal to f of 2 plus f of 1, which is 3c. And then we can just keep going up and up and up in this manner. And then we get like f of 4 is equal to 4c, f of 5 is equal to 5c, and so on and so forth. And in general, if we keep increasing by 1, we end up with f of n is equal to cn for all positive integers n. So this is already super, super powerful. And What if we have negative integers instead? Well, we can just go in reverse then. Like f of y plus 1 is equal to f of y plus c, means f of y is equal to f of y plus 1 minus c. And then if we make this one equal to 0, we get this is negative 1. If this is negative 1, negative 2, so on and so forth. So we can just keep going backwards in this way as well. So therefore we have f of n equals cn for all integers n. And now the obvious question is, can we extend this to the rational numbers? And there's nothing super generic we can prove about f, which is a substep of this step 3 here. So let's go ahead and move on to the next step. And this is to clean up all the mess we have. So I'm going to go ahead and put in f of n equals cn for all integers n. Now our next step is to clean up all the mess we have. So we want to show that it works for rational numbers as well. And we're super convinced that f of x equals cx is the only solution. So now let's go ahead and plug in some more things to see what we can do. So notice we haven't really tried y equals x yet. And that's another basic thing we could try. So when we do that, we get f of 2x is equal to 2f of x. And this is already super, super weird, because what if this one here is equal to an integer? Like for example, what if f of 2x here, what if 2x is 1? Then x is 1/2. Then we have f of 1 equals 2 f of 1/2, or f of 1/2 is c over 2. So now we've showed that f of x equals cx for a non-integer. And that means that we have something special as well. And this means f of x, if we keep generalizing this so that we have this is an integer n, we have f of n over 2 is equal to cn over 2. So we went above and beyond and proved it for numbers that are not the integers. And can we generalize this idea? Well, yes, we can, in that we were working over the rational numbers. Because we're doing so, let's go ahead and write x equals p over q. Because we can do that with any rational number. This is an integer, and this is an integer as well. And we're going to assume that q is greater than 0. Then we know that f of 2x equals 2f of x. We want to somehow get something involving f of qx. And we can again try getting rid of that x from that there, and we get f of x plus f of q minus 1x. We remove another x, we get f of x plus f of q minus 2x, plus so on and so forth. And then what this amounts to, when we get rid of all of them, is qf of x. And then when we plug in x equals p over q, we get f of p is equal to qf of x, or f of x equals f of p over q, which is cp over q, which is cx. And therefore, we have shown that for this x, f of x equals cx. And this means that f of x is equal to cx for every single rational number x. And this cleans up the mess we have. And then finally, we need to check our solution, which is the fifth step. And as we checked at the beginning, we have cx plus y is equal to cx plus cy. So this indeed fits. And we have solved our functional equation. Now, this is a super important functional equation that has a very, very special name. It's called Cauchy's functional equation. And now let's go ahead and see how we would write this up in an actual Olympiad with a cleaner way to obtain negative integers. So the answer is f of x equals cx, which works because, as before, cx plus y is equal to cx plus cy. And then let's go ahead and solve this. let P of x, y be assertion. This is very, very important when writing up functional equation proofs because it will allow you to refer to your original equation with much more ease. With much more ease. And this is from personal experience. So let's go ahead and use this. So our first step, remember, is to use 0 and 0, or one of them is 0. So P of 0, 0 gives f of 0 equals to f of 0, which means f of 0 is equal to 0. Then we end up getting that P of x1 gives f of x plus 1 is equal to f of x plus 1, or plus f of 1. Now, motivated by our slope idea, let's go ahead and let f of 1 equal c. So that f of x plus 1 is equal to f of x plus c. So if we increase x by 1, we increase f of x by c. And this means that for any positive integer, we get f of n is equal to f of n minus 1 plus f of 1 is equal to f of n minus 2 plus f of 1 plus f of 1 is equal to f of n minus 2 plus 2f of 2, f of 1 I meant, plus so on and so forth, and we end up reducing it down to, so this is, it's equal to n f of 1, which is cn. And then we can generalize this to negative integers by using p of negative x, x, to get f of negative x plus f of x equals f of 0, which is 0. So f of x equals negative f of negative x. In other words, we can generalize this to all integers. In other words, f of n is equal to cn for all n integer. And now let's go ahead and write x equals p over q, where we have a fraction where q is greater than 0 and both are integers. Then p of x k minus 1 x for a general positive integer k gives f of kx is equal to f of k minus 1 x plus f of x. And by just repeating this process over and over again, and doing something similar to this over here, which I won't exactly write out for the sake of space, we get f of qx is equal to qf of x. This is equal to f of p is equal to cp equals qf of x, and then f of x equals c over x, no, cx. And this finishes the proof. So that's how you would write it up in an actual Olympiad. I have a more verbose write-up inside the handout, so you can check that out if you want to. So that's our first ever functional equation that we've solved. So now we are ready to solve our first example. Find all functions f from the rational numbers to itself, such that f of x plus f of t equals f of y plus f of z for all rational numbers here that form an arithmetic progression. So let's go ahead and perform each of our steps. So the first step is to try finding all the solutions. And let's go ahead and see what linear solutions there are. So suppose that we have f of x is equal to like ax plus b. Then what we want is ax plus b plus at plus b is equal to ay plus b plus az plus b. And then basically all the b's cancel out. And what remains is a times x plus t is equal to a times y plus t. And if a is non-zero, then it just cancels out as well. So we need x plus t, this should be z. We need x plus t equals y plus z. And is this true for numbers in an arithmetic progression? Well, we could set this one to be a, this one to be a plus d, where that's our common difference, a plus 2d, and a plus 3d. And because a plus 3d is a plus d plus a plus 2d, that gives us our solution. And therefore this condition holds. So this means that f of x equals ax plus b is a valid solution. So I'm going to go ahead and erase this over here and put it up here. So f of x equals ax plus b. Now we can move on to the second step, which is to plug some basic things in. So the first order of action is, how do we even deal with this arithmetic sequence property? Well, I kind of gave a spoiler here, and this is already pretty natural because that's what you do with an arithmetic sequence, but we just plug this in. So f of a plus f of a plus 3d is equal to f of a plus d plus f of a plus 2d. So we have this equation here, where a and d are rational numbers. So this problem seems to be very arithmetic sequence coded, as we'd expect. So let's try going further along this arithmetic sequence. Like, for example, what if we shift everything up by d? Then we get f of a plus d plus f of a plus 4d is equal to f of a plus 2d plus f of a plus 3d. Now we want to somehow combine these two equations. And the only terms that are not in common with each of these equations is this one here and this one here. But luckily they're pretty isolated. So let's go ahead and see if we can relate these to one another. So the common terms we have are a plus d, a plus 2d, and a plus 3d. Let's go ahead and solve for f of a plus 3d in the first one. And we get f of a plus 3d is equal to f of a plus d plus f of a plus 2d minus f of a. Then if we plug this into here, we get f of a plus d plus f of a plus 4d is equal to f of a plus 2d plus this entire thing when we plug it in, f of a plus d plus f of a plus 2d minus f of a. Now we're really lucky because these guys cancel out. And when we bring this term to the other side here, what results is 2f of a plus 2d is equal to f of a plus f of a plus 4d. And we have that a plus 2d is like in the middle of a and a plus 4d. So in other words, like 2 times f of the middle one is equal to f of the one of them plus f of the other. And because a and a plus 4d are pretty arbitrary, this is really saying that we have the midpoint. So 2f of x plus y over 2 is equal to f of x plus f of y. So we have this much simpler condition we can work with now. So we want to solve this. And it's basically like a midpoint condition, as I said earlier. Now, the important thing about this is that this side here only depends on x plus y. So we can make x plus y anything we'd want, or we could just keep x plus y fixed while changing this side here, and therefore it will not change. So for example, f of x plus f of y is equal to f of x plus 1 plus f of y minus 1, because their sum is still x plus y. And in particular, we can plug in something nice into this one again, and get this is f of x plus y plus f of 0. Now at this point, we're super frustrated, because this is super close to Cauchy's functional equation, f of x plus f of y equals f of x plus y from earlier, but we have this extra f of 0 term, and we don't know how to deal with it. And moreover, we know that the solution set over here is ax plus b. And this is not the solution set to the Cauchy functional equation. So we know that any attempt to try using the Cauchy functional equation right here immediately won't work. So what do? Are we stuck at this point? Well, remember when we were checking the solutions? And this is really important why checking the solutions is super, super important. When we check the solutions, you saw how the b canceled out and we just did not care about b at all. So that makes us think that if f works, then so does like f of x minus f of 0. In other words, we just shift everything down. Then this f of 0 term over here should end up canceling out. And indeed it does. So if f works, then so does f minus f of 0. So we can go ahead and define this function g of x equals f of x minus f of 0. And because g works, g also satisfies this equation. G of x plus g of y is equal to g of x plus y plus g of 0. But look, g of 0 is f of 0 minus f of 0, which is 0. So this term goes away. Aha! Now we have Cauchy's functional equation. And this means that g of x is equal to ax for some constant a. And then when we plug this back in, we get f of x equals g of x plus f of 0, which is ax plus b. And this finishes the proof. So this problem teaches us a bunch of things. And one thing is that we can always try modifying it in whatever way we can to get Cauchy's functional equation. And that means that we want to use what we know and use that to solve what we want to figure out. So now we have the question of how do we even solve functional equations? Most of them that we come across aren't as straightforward as just plugging a few specific values and finishing it off. You'll often need to plug in very specially crafted values in order to get a very meaningful result, or perform some very special tricks. And for example of what heuristics we can try, let's go ahead and solve the following problem from the 2024 USA JMO. And this is a really, really hard problem, so we're going to take our time with this. Find all functions f from the real numbers to itself that satisfy f of x squared minus y plus 2y f of x is equal to f of x plus f of y for all x and y in the real numbers. So now our first order of action is to find the solutions. So could f be linear? Well, you can go ahead and check for yourself that the only linear solution is actually f of x equals 0. So what could it be if it's not linear? Well, because it's not linear, let's go ahead and take a step up and look at quadratic. So suppose that we have like f of x is equal to ax squared plus bx plus c. And we plug this into our equation. Then we get that this left-hand side is like f of x squared minus y plus 2y f of x. And if we plug in this here, we get that the leading term is like ax to the fourth. That's like the x to the fourth one here. And then we have, this is like a plus c here. And then we have 2y f of x, and that doesn't really give a plus c anywhere. So we have plus c, and then plus a bunch of stuff. And then we have the other side, which is f of x plus f of y. And we want to try comparing the coefficients again. And if we do that, we end up getting like, this one here is like a times ax squared plus bx plus c squared plus b ax squared plus bx plus c plus c. And then this one is like ay squared plus by plus c. The leading term here is equal to a cubed x to the fourth. So by comparing the two leading coefficients, we get, because they're equal as polynomials, a cubed equals a, which means a equals 0, 1, or negative 1. Now, if a equals 0, then this term vanishes and it's linear, which means that it's just 0. So let's go ahead and deal with a equals 1 for now. So then we have over here, f of x is equal to x squared plus bx plus c. And let's see what we can do to figure out the value of c. Well, one thing we can try doing is one thing we can try doing is just expand it out. So we have x squared minus y squared plus b x squared minus y plus c plus 2y x squared minus y squared plus b x squared minus, or this should be x squared plus bx plus c. And then this is equal to f of x, which is like x squared plus bx plus c squared plus bx squared plus bx plus c plus y squared plus by plus c. And once again, we can try comparing the constant coefficients and keep comparing different coefficients until we get something useful. So for example, when we compare the constant coefficients, we get c is equal to this one c squared, this one is bc, and then this one here gives, these two give 2c. So c squared plus bc plus c is equal to 0. This is already pretty useful information because given c, we can determine the value of b, hopefully. And then we have this y term here, and we want to see what we can do with that. So we have like, this is negative by, and then this one here gives 2cy. And the only y we get here is this one here. And that means we have b is equal to negative 2c. And then we get c squared minus 2c squared plus c equals 0. So c equals 0 or 1. And then we can check that the case where it's 1 does not work, which means c equals 0. And that requires that the only quadratic solution in this case should be f of x equals x squared, because the other ones are 0. And if we plug into the equation, we discover that it indeed fits. Now we have the other case a equals negative 1, but luckily this isn't much harder, because then we get f of x equals negative x squared, and that also fits. So therefore, we so far have 3 solutions to our functional equation: f of x equals 0, f of x equals x squared, and f of x equals negative x squared. Now, we are already ahead of a lot of Now, at this point, we're already ahead of a lot of the contestants, since many of them didn't even find the third solution. And this is why it's so incredibly important to try your absolute best to find all the solutions to a functional equation. Otherwise, you're going to try proving all the wrong claims. So now I've written the solutions up here in the right corner. So let's try proving that they are the only ones. So we first need to plug in some basic things. So let's go ahead and try plugging in x equals y equals 0 to start. Then what we get is like f of 0 is equal to, because this term is 0, f of 0 plus f of 0. And surprisingly enough, the f of 0 terms cancel out. So what this results in is f of 0 is equal to 0. So this is already pretty useful right off the bat. And now what do we do? Well, we have f of 0 is equal to 0, and we have this f of x term here. So it makes sense if we just plug in x equals 0 so that this term vanishes. And what we get is f of negative y plus 2y f of 0 is equal to f of y. Now, we still have this very, very pesky 2y f of 0 term in the front. So if we could prove that f of 0 equals 0, then this could be super, super useful. And moreover, all of these solutions we found satisfy f of 0 equals 0. So it's not like we're trying to strive for a lost cause. Because if we have like x squared plus 1 here, then proving f of x equals 0, or f of 0 equals 0 I meant, won't work at all. And therefore, we can actually try proving that f of 0 equals 0. And this is something reasonable to prove at some point. But for now, let's go ahead and set it aside. So one thing to remember is when we plugged in x equals y equals 0, this term here and this term here canceled out. So we want to see if they can cancel out in a more general case. So we have x squared minus y is equal to y, because then these two arguments would be equal and we'd be fine. Then when we solve, we get y equals x squared over 2. So let's go ahead and plug this in. So y equals x squared over 2. We get, by our command, these two terms cancel out. And that's because that's how we engineered y. And what's left is f of x is equal to x squared f of x. And this is already a pretty useful identity that we could try using later on. Now, going back to what we had above, how can we try using this to find the value of f of 0? Because remember, we want to prove that f of 0 equals 0 as to simplify this here. Well, if we try plugging in x equals 0 to get that f of 0 on this side, we get f of 0 is equal to 0, which is old news. So we can't really do that. But what if we try plugging in x equals f of 0, because f of 0 is 0? Then this should give f of 0 is 0, so that's 0. And that's equal to f of 0 squared times f of 0. But that's 0 as well. So therefore, this is 0. And hence, we have f of 0 is 0. And we can end up simplifying this over here and get f of y is equal to f of negative y for all real numbers y. And remember, we also have f of x equals x squared f of x. And now we're in business. So what else can we try plugging in? Well, we already tried x equals 0 because that's how we got this fact here. So let's try y equals 0. Then we have f of x squared, and this becomes 0, is equal to f of x plus f of y, or f of 0, which is 0. And we have that this here is equal to this here. And thus we have like this very like magical identity sort of thing, which is f of x is equal to f of x squared is equal to x squared f of x. So with this identity we have here, we can basically, because we have f of x, we can basically undo applications of f in this way. So we can turn 2 applications of f into 1. So what if we have 3 applications of f? f of x. Then how can we simplify this? Well, one way is we could just treat it as f of x. And when we treat it as such, we have f of x is f of x squared, which is also f of x squared f of x. Now we can't really do much with this with our identity, But we can also try using the identity on x squared now. And this becomes f of x to the fourth, which is also x to the fourth f of x squared. And then f of x squared here, as we know, is x to the fourth times x squared f of x, which is x to the sixth f of x. And we know that this is f of x. Now another way we can evaluate this is that we do f of x. So we're basically plugging in f of x into f of x. And when we do that, we get, by the identity, it's f of x squared, which is also f of x squared f of x. Now we can't really do much with this one, but for this one, because we have f of x, we end up getting f of x squared times f of x squared here. But again, that's not super useful. So we can do x squared f of x. So x squared f of x cubed. Now, because we just evaluated the same thing in two different ways, we therefore have x to the sixth f of x is equal to x squared f of x all cubed. And then if you solve for f of x in this equation, you end up getting that f of x equals 0, x squared, and negative x squared. And therefore, we have solved the functional equation. Or have we? After all, the only thing we proved is that f of x equals 0, or f of x equals x squared, or f of x equals a negative x squared for every individual x. We haven't proved that one of these must hold for all the x. We could just keep mixing and matching if we wanted to, and we could still get a very weird solution. So we have to resolve this very weird issue. And this is known as the pointwise trap, which I alluded to earlier. So how do we fix a pointwise trap? Well, if we want to fix it, we want to try assuming that we found a super weird function f that satisfies it. For example, we could have like f of a equals a squared for some number a, and we could have f of b is equal to 0. And we have to assume that a and b are non-zero. Think about why. Okay, so suppose we have our a and b such that f of a equals a squared and f of b equals 0. Let's see what we can do with f of b equals 0. Then when we try plugging in this b to our equation, we get, like, when we plug in x equals b, f of b squared minus y plus 2y f of b, which is 0, is f of b, which is again 0, plus f of y. So therefore we have, this is f of y. And this is already pretty useful, because now we have that it's symmetric across this other point instead of just negative y. But now here's the cool thing. We can use this fact here to solve this one here, because we know that this one is either positive this squared, 0, or negative this squared. So we can just take all the cases. For one, what happens if this is equal to 0? Then we know that this is also equal to 0. And that's like fine by this one here. Now, what if this one here is equal to b squared minus y squared? Then this could either be y squared, 0, or negative y squared. If it's y squared, then we have that b to the fourth minus 2b squared y is equal to 0, or y is equal to b squared over 2. So that might cause an issue for us later on. Now, what if it was equal to 0? then we would have y is equal to b squared. And that might also cause an issue. And then finally, what if it was equal to negative b squared, negative y squared? Then this one is non-negative, this one is non-positive, and that requires y equals 0. So again, we get a slight issue. So therefore, the only really weird cases that we need to resolve are the cases where y equals b squared over 2 and y equals b squared. Otherwise, for all other y, we have f of y equals 0. Well, for y equals b squared, we just plug this in here actually, and we get f of b squared is f of 0. So that just goes away. So f of y is equal to 0 for all y except for this super weird value, which is b squared over 2. But then we can just change the value of b we used earlier to get from this f of b equals 0, and then just get this one is 0. For example, we could choose like b to the power of 1434 plus 1, and get that this one here returns 0. And therefore, if f of b is 0 for a non-zero b, we have shown that f is identically 0. So now we can assume that f of b is not equal to 0 for any other b other than 0. So then we have another weird case where suppose f of a squared or f of a is equal to a squared and f of b is equal to negative b squared. Then what we want to do is try plugging in a and b for x and y in our equation. Then what this ends up giving us is f of a squared minus b plus 2 times b f of a, so 2ba squared, is equal to f of x, so that's f of a squared, plus f of y, which is f of b, which is minus b squared. And what is f of a squared equal to? Well, remember our identity from earlier, which is that this is also a squared f of a, and that's a to the 4th. So we end up getting that this is a to the 4th minus b squared, or f of a squared minus b is equal to a to the 4th minus 2b a squared minus 2b squared. Minus b squared, I meant. And now we can use the fact that f only has 3 distinct choices again. Well, technically 2 from what we did above, because this can equal 0, unless b equals a squared. And that just gets resolved by plugging in over here. Now, anyways, suppose that we have that this is a squared minus b squared. This is a 2b a squared minus b squared. And then when we expand everything out, we get b equals 0, which is bad. So therefore, we must have that this is negative a squared minus b squared, which is a to the 4th minus 2ba squared minus b squared. And when we solve for a and b, we end up getting that b is equal to a squared over 2, just like before. And then we have the only value of x that gets sent to the negative of its square is a squared over is equal to just the a squared over 2 here. And then every single other number must get sent to its square. And then we can just choose a to be something different, just like we did earlier, and get a contradiction again. And an exercise for you is to work out the rest of the details. And therefore, we have resolved the entire pointwise trap, which means the only solution are these ones claimed here. We don't have any weird ones. And that solves the functional equation. Now, let's go ahead and try looking for a simpler solution which avoids the pointwise trap. I'm just going to present it right now for the sake of time. And I could have included the solution to begin with, but I like the earlier approach because it exemplifies many functional equation philosophies, which I'll get to in a bit. So here's a clean solution. So as before, we end up getting that f of x is equal to f of x squared is equal to x squared f of x. This is our magic identity. Now, you can go back to our functional equation from earlier and look at that when we read up the proof. So now we have that f of x squared minus y plus 2y f of x is equal to f of x squared plus f of y by this identity. And then we can plug in y equals t squared to get f of x squared minus t squared plus 2t squared f of x is equal to f of x squared plus f of t squared. But now this side here is symmetric in x and t. So that means if we swap x and t, this side should remain the same. So this is also equal to f of t squared minus x squared plus 2x squared f of t. But then recall that because f is even, we have these two cancel out because it's like f of a is f of negative a. And what remains is t squared f of x is equal to x squared f of t, or f of x over x squared is equal to f of t over t squared. And this is true for all real numbers x and t, which are not 0. So which means that because all these ratios are equal, they must be equal to some constant c. And then f of t is equal to ct squared for all t. And this even holds for t equals 0 because f of 0 is 0. And now we just plug this into our original functional equation to get c is 0, 1, or negative 1. And we finish the problem. Now, I really like this problem because it introduces many key heuristics, which I'm going to go ahead and state. So one of them is that 0 is your friend. And you have to use it well, unless you can't use it at all, which we're going to be exploring in a few videos. Then the second thing is if we know something about f of x, then try saying something about f of x. Because you can calculate this in two ways, just like how we did to get the solution set. And then the third one here is to try canceling terms from either side. Because by canceling terms, we can end up reducing the total number of terms and hopefully get something much easier to work with. Just like how we did to get f of x is x squared f of x. Then the fourth thing is to beware the pointwise. And even though you may know about the pointwise, that doesn't mean you're entirely immune to it. Please be careful. And the other day I forgot the pointwise trap on a functional inequality I was faced with, so yeah, be careful. And the fifth thing is to exploit asymmetry. Meaning that if one side is symmetric and the other one is not, use that to your advantage, just like how we did in the simple solution. All right, so there's not going to be our typical end of video example, which you're going to work on your own, but I provided a bunch of exercises at the end of the handout for you to practice the functional equation techniques, plus some ones which aren't listed above that I listed earlier, which you should try discovering on your own. And as I said earlier, you'll have to try coming up with new ideas on the fly as you solve harder ones. So thank you so much for watching this video. Please subscribe if you'd like to see more, and hope to see you guys in the next one.